Swayam Prabha. Digital India. Educated India.
Okay. So you have looked at some kind of frequency estimation from data streams already? No? You need to have a conversation with your TAs at some point. Okay, fine. So the only point I wanted to make is a completely different setting. Even if you have seen anything before, forget about it. I am not talking about counting on streams now. Okay, so I am talking about counting in very large databases. Right? We are talking about looking at frequent patterns in, say, Amazon's purchase data or something like that. Right? Very large database. So that's basically what we are going to do, right? So this whole how people have heard of the term data mining. Have you? Right. So this whole field of data mining, right? The first time people used the word mining was to this task of what is called association rule discovery. Right. The very first time people used the word mining with data, right, was when they did association rule mining. That's what they called it, right? And the idea here is that you have to identify items that are bought together by many customers. It's called the market basket model. So you take a basket to the market. How many of you know of this market basket business? 2, 3. Okay, I hallucinated the third hand, but thanks for putting it up and making it true. Okay. Okay. Sure. The idea is very simple, right? So think of it, you go to a shop, you're taking a basket with you, right? Going to some supermarket, right? You take a basket with you and start putting things into the basket, right? So then you come back and put the basket, that's all the purchases you have made, right? So that is considered like a transaction, right? So the transaction has a lot of items that you have bought together, right? So a transaction is going to consist of some subset of a large set of items that constitute your inventory. Okay. So somebody wants to know what are the items that people buy together in their shop, right? And so that's basically where the frequent pattern comes in, and the association rules was something that people were using to make decisions based on the frequent pattern, right? So what does it mean? So if you find that a lot of people buy, say, milk and bread together when they go to a shop, right? A lot of people buy milk and bread together. So you can create a rule that says that, hey, if this guy has bought milk, then he is likely to buy bread. So how did you come up with that conclusion? It's because milk and bread was bought together a lot of times, right? Okay, so that's basically the idea. So this is what people talk about as association rule discovery. And so once you have these patterns, right, that milk and bread were bought together often, right, it turns out you can come up with these association rules fairly straightforward, right? So that's what I'm going to talk about initially. The hard problem is coming up with the frequent pairs, right, coming up with the frequent item sets, right? So it turns out that it's because everything is combinatorial now, right? So I have a set of items K, then I can look at 2 items bought together, 3 items bought together, 4 items bought together. Now you immediately see the number of candidates items becomes much larger. So now for me to count how many pairs of items were bought together, I have to generate the entire space of candidates, right? And that can become fairly large very quickly, right? For n equal to 2, 3, 4, 5, it can become very large, right? So it just becomes hard to even enumerate possible frequent patterns before I verify whether they are frequent or not, right? So doing it naively can become pretty hard, but once I have these frequent sets, I can always create rules out of them. So milk and bread are frequent, so I can say milk implies bread and bread implies milk. I can create 2 rules, right? Let's say milk, bread and eggs are frequent, then I can say milk and bread implies egg, or milk implies bread and egg, all kinds of combinations. I can do all these rules, but I need to know that they are frequent first. So the biggest challenge is in counting. So we'll just go through the first few slides and then we'll come back after the coffee break and look at how we actually do the counting efficiently. Okay. So the idea, originally they started doing this on market basket data and actually on supermarket sales data, and therefore the name market basket analysis stuck to it, right? And this is actually a classical rule that people discovered initially and it created a lot of buzz, right? Somebody buys diaper and milk, they are likely to buy beer. Let's assume they're talking about baby diapers. Okay. And so actually supermarkets took these ideas and then tried to kind of at the end of the aisle where you have all these baby products, at the end, not in the middle of the baby products, but at the end you will see some beer cans stacked. So somebody goes and buys those things and they walk away, they need to pick these beers. What's that? Yeah. Anyway, so I mean, if you want to know what the reason is, somebody actually analyzed this to figure out why this was happening, and it turns out that these guys were all very, the US, right? They're all big on Sunday night or Monday night football or something. And there's some football things that they are very big on, right? So whenever they come for their weekend purchases, right, they typically come once in the week to stack up on diapers and milk and things like that, and then they say, okay, I need to get beer because all my friends are going to come and watch the match. So typically married guys were throwing all these parties. Of course, young guys would probably go out and party, right? They're not going to throw it at home. So diaper and milk implies that they are married. Okay. And they're likely to buy beer after that. I mean, I was saying that in all seriousness. I didn't expect it to be funny, but anyway, so that's an indicator that they are likely to be married and they have a house and they have. So it actually is a valid thing. There is actual reason for it. Is not a statistical anomaly. If you dig into it, there is actually a reason for why that rule appears. But it's not something that will pop up to the top of your head. But from now on, I'm pretty sure it's going to pop up to the top of your head, right? Please don't go and tell your parents anything about milk and beer. Anyway, so the point is there will be a lot of these. These are basically your transactions. Right? This is how the data is going to look like. So you're going to have these transactions, and you're going to have millions of these transactions. Right? You're going to have millions of these transactions. Right? And then basically the goal is to discover rules like this. Milk implies Coke, and diaper and milk implies beer and things like that, right? And likewise in Amazon, right? People who bought XYZ tend to buy V and W and all that, right? So the first application we already looked at. This is on this kind of market basket analysis, right? So this is a tie-in tricks. For example, you run a sale on diapers, but you raise the price on beer. So people are coming into your shop thinking they have a sale on diapers, and then they're going to pick up the beer, and then they're going to, very unlikely that they're going to go to a different shop to pick up the beer, right? So this is why like statue. Yeah. So if you're going to actually, this is the motivation for why this has to happen frequently, because you can always discover this kind of associations, but they might be very infrequent. In fact, there is this whole area of actually trying to do infrequent but significant association rule mining. Right? These don't happen often, right? But when they happen, it's like a very, for example, some kind of an security breach. So you are monitoring network traffic that is coming in, right? Security breaches are going to happen very rarely. So they are not going to be frequent patterns. But whenever a certain activity happens, the probability of a security breach goes up from 0 to say 0.17. That's a significant jump. Right? Because earlier there was no security breach, now there is a chance that a security breach can happen. Even though the whole thing is a very, very rare occurrence, it's a significant association. So there is a whole area where people look at significant association mining. Right? So This is not it, right? We are now talking about frequent pattern mining because we are interested in these algorithms for counting data, right? This whole the association rule is just a motivation for why we need to look at frequency, because if you really want to monetize these rules and have some kind of an outcome from this, you need it to be frequent, right? So here is another example. You can see that there is some academic involved in writing all these books, right? They're very worried about plagiarism and other things all over. Right? So here's another example. So the baskets could be sentences, right? Items could be documents containing those sentences. It's a little weird. It's flipped around if you think about it, right? So what am I interested in finding? I'm interested in finding items that co-occur frequently across multiple baskets, right? So what does it mean here? If two items occur in like 80% of the baskets together, what does it mean? So items or sentences, that means 80% of the items or documents, that means 80% of the sentences are common between these two documents. So that means they are copied, right, or plagiarized or some very high similarity. This is another way of measuring similarities, right? So we are talking about but this is flipped around. This example is given just to make you appreciate that it is not always a basket with items in it, right? The transaction is not a basket with items in it. It can be flipped around. So the items are documents and baskets or sentences. So your items contain baskets, but still we are still counting the co-occurrence of items in baskets. So that's a thing, right? And finally, here is another one. Items are drugs and side effects, right? Baskets are patients, right? Can be used direct combinations of drugs that result in particular side effect across many different patients. So it occurs frequently in a lot of patients, right? But then you also have to look at not just the presence of an item, but also as the absence of an item. So it shouldn't be just drug and side effect, it should be not drug and side effect also should be there. So we have to pay attention to the fact that not drug is an item, not given the drug is an item. So there are various things that can be done. So what we will do now is basically look at frequent item sets very quickly. Okay, so we first count what is called the support, right? The support is essentially how many transactions in which a set of items occurred, right? So I also need to point out that the frequent this whole association rule mining community call a set of items as item set. Okay, so basically you count the support of every item set that you are interested in, and this support is basically the number of transactions in which that item set has occurred. Right. So sometimes the support can be a fraction of the total number of baskets, or sometimes it can just be the number of things, right? So given a support threshold, right, the set of items that appear in at least S baskets, right, where S is a threshold, are called frequent item sets. Okay. Yeah, this animation I will go very quickly through, but you can see that. So milk, Coke, Pepsi, beer, juice. So these are all the transactions we have. We have 8 transactions, and we say a support threshold is about 3, right? And the frequent item sets, obviously M, C, B, J are all frequent. Okay, not a Pepsi country. And MB is frequent, BC is frequent, CJ is frequent. There are 3 things that have a CJ, right? Anything else is not frequent. So what else is not frequent? Milk and juice is not frequent, for example. It appears only in 2 transactions. So the association rules are basically formed of this form. I1 to Ik, which is my item set, implies J means that the meaning of the rule is the following: if the basket contains all of these k elements, then it is likely to contain J. Okay. What it really means is the subset I1 to Ik comma J was frequent, right? Because unless it was frequent, that association is of no interest to me. Okay. So, there are many rules I could generate, right. So, for example, this I1 to Ik implies j, I can also say any subset of that I1 I2 implies I3 to Ij, that is also a rule I can create, right. There are many different rules that I can create. So, what I am interested in are rules that have certain other properties. The first thing I want to look at is something called confidence, right. So, the confidence of the rule is basically the support of I union j divided by support of I. So, the first of all, it has to be frequent, that does not mean much, right. So, suppose I say that I union j occurs in 5 baskets. So, the threshold is 3. So, 5 is frequent, right, but I, that is without the j, right, occurs in 300 baskets, right. I union j occurs in 15 baskets, I alone occurs in 300 baskets. That is not a really strong rule, right. Out of the 300 times I have bought I, 15 times I have bought j. I will not want to call that as an implication. Right. So, my I union j also has to be high. Suppose I union j is 15 and I is 15, that is a very strong implication, right. So, that is the kind of rules I want. So, that is basically confident. Like that, there are many measures that you can define on how these association rules come up. There is confidence, there is lift, there is interest, right. There are many metrics that you can define. Since I am not getting into the association rule part of it, I am skipping all of that, right. And so, the goal is we want to find association rules with at least some support, right, and a confidence greater than or equal to C, right. So, the support of an association rule, right, is literally support of I, right. Is the support of I is called the support of the association rule itself, right. Yeah. If this rule has a high support and high confidence, then both of these will have to be frequent, right. But the question is, how do we find these frequent item sets, and we have to figure out how to count these frequent item sets. So, let us start with the frequent item sets part. So, the idea is that first thing is typically many of these things are stored in flat files. Okay, so what are flat files? Basically just a listing of items like that, and every time there is a end of a transaction, you probably have a -1, right, and so on and so forth. It is not like not like reading this and computing things with it is easy, right. And so, we have many baskets and many items, and so typically you end up having to use something like k nested loops to generate all sets of size k, right, and you are going to read this and generate this. This can become computationally pretty intensive, right. So, what we really want to do is figure out a way, right. So, one thing that you have to remember, right. So, if I have to determine if a set of size k is frequent or not, the first thing I have to do is know what are the elements in the set of size k, right. Only then I can go and compare if that is frequent or not. So, if I have to generate each and every element of a particular size, right, before I can actually go and count if they are frequent or not, right. And typically I will have to store that all the elements that I am going to generate in memory before I go and count. Otherwise, if I am going to generate one k set one at a time and then count if it is there in the baskets, right, then I have to go through the baskets every time I generate this k thing, right. So, it will be good to have the set of k size subsets for which I am going to count. Does that make sense, right. So, I want to make sure that at the end of the day I only count the occurrences of subsets which have a chance of being frequent. Like we talked about candidate pairs earlier, right, in locality sensitive hashing. I would like to have a way of generating candidate pairs when I am doing frequent item set mining, because if I am going to count for every possible subset starting from size 1, 2, 3, 4 up till whatever, right, this can become quickly intractable, right. And another thing to remember is that since this is not organized in any efficient manner and these are flat lists, right, the biggest cost is the number of times I have to go to the disk and read this list. It's not like I can read the entire transaction list and keep it in memory. It's typically too large for that. So typically I would like to minimize the number of passes, right. I need to go over the data in memory. So this is the second criterion that we'll have to think about, right. So how to minimize the number of passes the algorithm makes over the data, right. And so many of these algorithms, the memory becomes a bottleneck. So you can't store things in memory, right. So for example, I have generated my list of baskets for which I am going to count, right, and I start counting. But it turns out that if I make this like let's say I am looking at 3 subsets, right, 3 item sets, that means that subsets of size 3, right, and suppose I have like a million items that are there in my inventory. So it's literally like million choose 3 subsets that I could potentially have, and I start counting these, right. Just retaining all the counts, right, can become pretty memory intensive, right. And then if I want to do this for subsets of size 4, then it becomes even more memory intensive, right. So one option is to say that okay, I am going to read this a chunk at a time, right. So I will first read the first k, whatever first n entries in this and then count them and then swap in and out, right. Then it can become quickly become a disaster. Why? So there are 2 things that could happen. One, you are trying to minimize the number of passes through the data. So as you are reading the data, once you discover some element, you might want to add a 1 to the count, but that current count of that element might be in the disk, not in main memory. So you will swap that in, swap something else out, right, and then add, and then the next element that you want to count could have gotten swapped out now, right. There is no way to order these because your data is in a flat file, it is not ordered by any mechanism. So the elements could come in any random order when you are counting them, right. So what might happen is you'll end up spending your entire time just swapping in and out, right. On the other hand, you could just try to minimize the number of swaps. How can you do that? By doing more and more passes through the data. So first you keep some n counts in memory, go through the data, only count those n elements, right, and then swap that out, get the next n counts, go through the data again. Remember, but every pass that you make through the data is adding significant amount of cost. So we don't want to do that as well, right. So swapping counts in and out is also not a great idea. So is there a better way of doing it, right? So it turns out we are going to focus on finding pairs in the first place, right, counting pairs of elements. Why? So it turns out if you take out all possible pairs of elements, right, a larger fraction of them turn out to be frequent than if you take all possible triplets, right. So that's kind of obvious, right, and it's not a surprise, right. So 2 things are more likely to occur together than 3 things occurring together, and then 4 things occurring together, then 5 things occurring together, and so on and so forth, right. So in fact the probabilities of some of these being frequent starts dropping very rapidly, and we can come up with clever ways of pruning the candidate sets, right. The candidate pairs, it's hard to prune, right, you will have a lot of candidate pairs, right, but the candidate triples will be a lot smaller, the candidate 4 triples will be even smaller. So once you are able to count your pairs in memory successfully, right, then you can count triples, 4 triples and other things successfully. So we will come to all of that later, but right now we will focus on just getting the pairs out, right, and after that easy ways to handle a bunch of things, right. So the goal is we have to generate all item sets, no go about it, but maybe we can generate it and quickly test and throw it away and not maintain counts, right. So we can remember only those item sets for which we have to do the counting. So that's basically what we're going to try, right. So we can, the naive algorithm for doing pairs is read the file once, right, count in main memory occurrence of each pair, right, and for each basket you can generate your n choose 2 pairs just by 2 nested loops, right, and then you have the set of pairs and then you can count, right. But this will not work if even the number of items squared, right, that basically your n choose 2, right, if that exceeds main memory the naive approach will not work, right. And so just to give you an idea, so there could be like 10 power 5 items, which is a small number really, right. So Walmart has actually a larger inventory nowadays than 100,000, and each count is a 4-byte integer. So basically you will need something like 20 gigs of main memory if you would like to count each pair of items from Walmart, right. Of course 20 gigs you probably have, but remember you are sharing this with a whole bunch of other applications, so you might yourself application might not get 20 gigs and things like that, right. Okay. So let us assume that you can implement the naive algorithm. Next comes the question, so how do you count, how do you store the pairs, right. You can count all pairs by using some kind of a triangular matrix, right, and then you can basically use the ij index of the pairs to figure out where you index into this triangular matrix to get the entry, or you can use the sparse matrix representation. People are familiar with the sparse matrix representation, right. So you can use a sparse matrix representation where basically it is a table of triples I, j and c, right. So I and j are basically the matrix entry, and then c is the actual value in the location, right. So the count is going to need 4 bytes per count, while this will need something like 12 bytes per entry, right. It will need something like 12 bytes per entry for the triples, right. So it will be something like this. So triangular matrix will be completely filled up, whether you use it or not you will have 4 bytes per entry, and the triples will have only, for the counts that you are using you will have only 12 bytes. So basically rough back of the envelope calculation. So using the sparse matrix is better if only less than 1/3 of the pairs actually occur in the data, right. If the more than 1/3 occur, you will actually spend less memory if you use the triangular matrix. Okay, that's simple. But this is the biggest problem is the naive approach does not work, right. We have too many items, so the pairs do not fit into the memory, right. So can we do better? The first trick is the a priori algorithm, right. So people are familiar with the a priori algorithm. The same people who have heard of association rule mining, okay. Sure, okay, fine. The idea is very simple. So it's a 2-pass approach, right, not a 1-pass approach. So the one that we looked at earlier, the naive algorithm, is a 1-pass approach if you think about it, right. What I did was I initially generated all pairs of items in memory and then just counted them as I did 1 pass through the data. Now a priori limits the amount of main memory needed, but trade off is it is going to need 2 passes over the data, okay. And the key idea that we use is called the a priori property, which is a monotonicity property. So it's stated like this, when we actually use the contrapositive, but it is stated like this: if a set of items I appears at least s times, every subset of I has to appear at least s times. Yeah, you can say duh, but that's an observation that they turned it into the contrapositive. What is the contrapositive? If an item I does not appear in S baskets, then no pair that includes I can appear in S baskets. Right. You can generalize this. So if a subset, right, I does not appear in at least S transactions, right, then no set that contains I as a subset can appear in S transactions, right. Is that clear? Right. So you have this kind of a lattice here. So you have ABC have to be frequent, for AB or AC or BC to be frequent. So, for example, here A and B are frequent, C is not frequent, therefore, AC and BC will not be frequent, right. So, a priori uses this idea. So, basically you first count ABC in the first pass, right, and then the second pass you only count for those pairs for which both the elements appeared in the frequent list in the first pass. Okay. So, now I can only count for AB, so I do not have to count AC and BC, and extending the a priori algorithm I do not have to count ABC at all because only AB is frequent, right, but ABC has BC and AC has subsets, both of which are not frequent. So, I do not have to count for ABC at all. So, basically I will count AB, A, B, C separately and then AB and then I am done. I have found all the frequent item sets, even I mean whether AB is frequent or not. So, I am done. So, this is basically the idea behind a priori, right. So, in pass 1, right, I read the baskets and count in main memory the each individual item, right. Now, this requires memory only proportional to the number of items, not number of items squared, right. It requires memory proportional to the number of items. So, items that appear greater than or equal to S times are frequent items, right. Read baskets again and count in main memory only those pairs where both elements are frequent, and it requires memory proportional to the square of the frequent items. Of course, this whole thing falls apart if every item in my inventory was frequent, right. That means I'll still end up with this, but typically that's not the case, right. But you also need to remember what are the items that you are counting. So, earlier I could just count every pair that is coming in because I knew that I am interested in counting every pair of items, but now I need to know which pairs are interesting. So, I will only count those. So, I need to store the pairs that I am counting as well, right, as well as the counts themselves. So, that is basically what the a priori algorithm is. So, that is basically what happens here. So, in pass 1, let us say I have so much memory, right. So, in pass 1 I count the items, individual items, I just get their counts, right, and then from there I know what are the frequent items, right. So, in pass 2 I remember what the frequent items are. So, that is what we said here, right. You need a list of the frequent items, then you count the pairs of frequent items in pass 2. So, how do we store the list of frequent items here? So, I can actually use the triangular matrix because we are assuming that more than 1/3 of the items are frequent, right. If less than 1/3 of the items, I am not talking about item sets here, right, I am talking about individual items. So, there is a good chance that at least 1/3 of the items are frequent, right. So, I want to store it as a triangular matrix, but the thing with the triangular matrix is I want it to be dense, right. Only then I get the advantage of using a triangular matrix. So, now what will happen is if only a small fraction of the elements are frequent, right. So, let us say 30% of the elements are frequent, then what will happen is I will have a lot of rows for which I do not want to do any counts. So, what we do in that case is something simple. Let us say I had 1, 2, 3, 4, 5, right, I had like 5 items and only 1 and 3 are frequent, 2, 4, 5 are not frequent, I have gotten rid of them, right. So, what will I do is I will basically create an upper triangular matrix with 1, 3 and 1, 3 as my entries, right, for storing the count. But the challenge here is it is a matrix, right. So, I will anyway have a index for 2, 1 and 2, 2, 2, 3 and all that. So, basically what I do is I do a remapping, I take 1 to 1 prime, 3 to 2 prime, and now this matrix will be in terms of 1 prime, 2 prime, it will not be in terms of the original numbering, right, I will now renumber it. So, that renumbering I store here, right. So, I take some additional space, I store the frequent items, I store the renumbering, so that this thing can be done as a matrix. Okay. So, this is how the a priori process goes. So, for every k, so first I started with k equal to 1, now we looked at k equal to 2, then going forward, right. For every k I create 2 sets of k tuples. So, the first set is called the candidate set of k tuples. These are the ones that might be frequent, right. So, and then I have Lk, which is the set of truly frequent k tuples. Right. Ck is the candidate k tuples, Lk is the set of truly frequent k tuples, right. So, how do I do that? I first take in all items, right, obviously, right, that is my candidate set of 1 tuples. I have nothing to filter until I have done some counting. Then I count, then I get the set of truly frequent items, right. Now, what I do is I create all pairs of items from L1, that is basically what we did here, right. We create all pairs of items from L1, that constitutes my candidate set for k equal to 2. Then I count the pairs, that is what we are doing in the triangle there, we are counting the pairs, right, and then the frequent ones among the pairs gives me my set L2, right. Now, I will construct my candidate set C3, right. There are multiple ways in which you can construct C3, right. So, one way to construct C3 is to take C2, right, and C1, and then just say, okay, I am going to do a, add every frequent item that is not there in this C2 in this pair, I am going to add that to this pair, right. I can create a set of candidates like that, right. And so, what we did here, we took Bm, right, and then so BCJ was generated by adding J to this, B and BMJ was generated by adding J to this, like that, right. So, we just keep going, right, that should be BCJ, right. So, we take these items and we add from L1, right. So, we add one item to each of the possible item sets and create my candidate for the next round, right. This is cheaper to create, I can do a little bit more work. And how can I do that? So, for everything I created in C3, I can look at the, so the BC should be there, CM should be there, BM should be there, okay, they are there. What about BCG? So, BJ is not there, right. So, BCG can never be frequent. So, what I can do is I can basically look at L2, right, and prune C3 further. So, what we have done now right now is we have taken L2 and L1 and constructed C3. That is the cheapest way of constructing C3, right, but I can go through C3 and prune it further. In fact, only BCM should be in C3 and it turns out only BCM is in L3. So, if I want to go from L3 to C4, I can still do that, but going from L3 to L1, combining L3 and L1. So, basically I can generate a C4 by saying BCMJ, right, but we know that it can't be frequent, we know that for sure because J does not appear in any of the smaller frequent item sets, right. So, we can do that kind of a pruning. So, this is so there are many variations of a priori algorithm out there, right. So, I think the basic a priori algorithm was proposed sometime in the early 90s, right, and people have been working on this. Now, there are many different variations of frequent pattern mining algorithms that are out there, and there are as many different ways of implementing a priori, but the monotonicity property that we use, right, is been crucial for most of the algorithms. I mean, now there are algorithms that do not take advantage of the monotonicity property, they give that up in exchange for something, right. Given the trend that we have been having so far, what do they give up? Right. So, they might miscount some of the things or they might miss out on some frequent pairs and things like that, but they can do it a lot more efficiently. They can count for all possible k tuples in one pass and things like that. So, there are a lot of complicated algorithms that are out there, right. Okay, so we will stop with this slide. So, the thing with a priori algorithm is that literally you have to do one pass for each size k through the data. right? For large data set, there is still a bottleneck. You still don't get a efficient implementation, right? And so you need room in the main memory to count each candidate k tuple, right? So the more aggressive you are in generating the candidates, basically more pruning you do in generating the candidates, the more likely that this will run efficiently, right? And so this is the thing I wanted you to notice, right? For typical market basket data and reasonable support, and look at the reasonable support they are talking about. In practice, right, when I am talking about millions and millions of transactions, right, something is we call frequent, even it appears in 1% of the transaction. Suppose I am analyzing like 100 million transaction data, right. So 1% of the transactions is still a million transactions. So if an item occurs in a million transactions, I will call it a frequent item, right. So it is not like 30% or 50% or 80% is like a frequency threshold. Frequency thresholds are typically pretty small, and even those you have a significant pruning. Even this 1%, right, most items might not occur.